Yep. Yep. Thank you. So thank you very much for having me here. Thank you, Yavor. So yeah, while being in the University of Oregon for that time, I've decided that I have to be here. I have to find my way to Galois somehow. Uh, well, because this company is very well known in the Haskell community, and it's very important for us. So I was very interested in how things are going on here, and that's why I am here. And I will talk about Haskell, teaching Haskell, and this is, well, questions that I'd like to answer. But I have to say one thing. In fact, I think that we still don't know how to teach Haskell properly. And whenever someone tells you that he knows or she knows how to do that, I think that's a lie. Well, if we would know that, that would mean that Haskell would be the most popular programming language at this planet. But, well, it's not, definitely. And the reason is that, well, it's a hard language, and it is very difficult to teach it. And I know many approaches, and there will be no breakthrough in this talk. So actually, I will always tell, well, I am doing that this way, but maybe that's wrong. And I read a lot of books. I was trying to analyze a lot of online courses and other educational materials, and I always see some problems with them. So I'm never happy about how other people teach Haskell. I'm not happy about how I am teaching Haskell. So maybe there is a problem in the language. Maybe there is a problem with us. I don't know. So I will go quickly through the first three questions here, and I'll start with why teach Haskell, and then I will talk more about what and how I am doing in my courses in my own university back in Russia. Okay, so what should we teach? I believe that teaching Haskell itself is something that we don't actually need. Why on earth you would need Haskell? So, but we could use it as a teaching tool actually for teaching programming. Like, I mean, Haskell as a first programming language. You can teach that at school. I never did that by myself, but I know that there are experiments for doing exactly that, Haskell as a first programming language. And some people report absolute success. Some other people report absolute disaster with that. And I don't believe every one of them, actually, because, well, there is never total success or total disaster. But of course, there are always problems. But it is possible, and we can teach everything. We can teach working with files. We can teach imperative programming. We can teach functional programming in that course. So Haskell is good for everything like that. We can also teach functional programming with Haskell. So Haskell is the first functional language. This is actually an approach which I am taking in my university. So I don't teach Haskell, but I teach functional programming. I want to show how it is a good way to write programs in functional styles. So that's mainly about functional programming style. So we can give some information about high-order functions and maybe algebraic data types and stuff like that using Haskell. And in that case, we don't need any sophisticated Haskell features for doing that. Well, we could also teach industrial programming. Well, because it is possible to do something like logging or configuring your application or talking to databases, complex event processing, whatever. So every industrial practice can be done and can be taught using Haskell, and we can do that. And we can also use Haskell for teaching about the power of abstractions. And this is a topic which Haskell is especially good for, I believe. So the idea of a monad is just one example, which is well known in Haskell community, but we have much more abstractions. Like we have semigroups and monoids, and then you can find easily the Haskell library where request is constructed using monoids. You just add request fields, headers, HTTP headers, and stuff like that using semigroup operation. And then you have a fully constructed HTTP request. So, and abstraction is just monoids from abstract algebra. So we could imagine having a special course in abstractions in programming. And these abstractions are much better than abstractions in object-oriented programming, like patterns, object-oriented patterns, and stuff like that. So we can use Haskell for that. In fact, we can use Haskell for teaching some science. So, for example, type theory, and I've done several experiments with that. So you can teach type theory using Haskell, using GHC compiler internals, for example. So they have this core language inside it. And you can teach type theory, you can teach system F, you can teach all other things using Haskell as an example. So you just write a simple program in Haskell, and then you see how it is translated into lambda calculus. And you can teach lambda calculus with this tool. You can teach reductions and everything else using this Haskell as a teaching tool there. And there are other things that can be taught there. So, for example, in those dots, I can teach theory of computations with Haskell. I can use Haskell there too. And maybe someone of you knows there is a book from O'Reilly, I believe, computation theory of computations for programmers. And they use Ruby there. So they're teaching stuff like Turing machines, undecidability, complexity, using Ruby as an example. And I believe that's totally wrong approach, and Haskell would be much better for doing things like that. But still, you can do that. And I'm also I'm lecturing on the theory of computations. And of course, apart from Turing machine, which is mandatory for that course, I also give lambda calculus there as another model of computation. And of course, Haskell is very good for demonstrating things. We can write interpreter just in half of an hour and see a lot of interesting stuff with that. So I believe that Haskell can be used as a teaching tool for teaching all this stuff. And we don't need to teach Haskell itself. Because, well, if you say, well, let's learn some Haskell, but why? Why do you need that? Because, well, nobody uses Haskell at work. It's impossible to make money with Haskell, and there are many other problems. Well, maybe it is possible. I don't know how to do that. Okay, so then when should we teach Haskell? So again, we can teach that at many levels. So speaking about experiments of Haskell at school, I know only about high school experiments. Maybe we can do that earlier. Maybe not. I will show you one example from so-called Code World initiative. It's a library and a website for teaching Haskell and some other languages, and mainly about teaching programming with pictures. And that's a very good approach which can be used quite early, like elementary school, middle school, something like that. So it is possible, but I never did that by myself. We can teach that in college. For example, I was teaching Haskell for the second-year students and for the fourth-year students at the university. And of course, those courses, they're quite different. Of course, they know different things and they're interested in different things. Like when the fourth-year student, last-year university student, they don't think about any theory. They just think about how to get their job, the high salary, so that's what they're thinking about at that time. And when they're second-year students, they're willing to do some theory, they are interested in stuff like that, so these courses can be very different. It is also possible to teach that at the graduate school. For example, I was looking at one experiment at Northeastern University in Boston about 2 weeks ago. So there was a group of graduate students, and in programming languages, they have very strong programming languages lab there in Northeastern, and they were trying to get monads. So they don't want to teach, to learn Haskell. So just a group of graduate students, and they try to get monads because it's, well-known concept in programming language, and they're doing that. So it is possible that it can be interesting there. And then, of course, something which is extremely important for Haskell especially is lifelong learning. I think Haskell is a champion of the programming languages, which is learned by people who are doing something else for their professional job. Like they can write some JavaScript code at work or PHP, but then at weekends or in the evenings, they're trying to learn some Haskell. Well, because Haskell is popular for that. And I know many people like that who are trying to learn Haskell just for fun. And I don't know people who try to learn Java just for fun, for example. Never heard about that. So tell me if you know that example. So this is something and that you can do independently of your age. You can be old, you can be young, it doesn't matter. So you can learn Haskell, and that's why you need a lot of educational materials for doing that. So Haskell is good for that. And in fact, I found that different ages require absolutely different things in Haskell. Like when you are, I don't know, 40 or 50 years old, you may be interested in abstractions more. You want to know everything about profunctors and something sophisticated. If you are like 20 years old, you're not interested in that. Maybe you want to get your job done. So there is a big difference. And of course, you have to think about that when you approach this teaching all that stuff to those guys. And by the way, there are a lot of people who are mentoring Haskellers, studying Haskellers, and they also try to get what those people want, and then they give them exactly what they want. And it's very unusual for teaching other programming languages, I think. All right, and who? I'll just give you several very well-known examples of courses which are taught about Haskell, and I think these three courses are the most well-known. So one from Australia, Data 61 or NICTA, with Tony Morris, Mark Hibbert. It's very well-known. You can find it on GitHub, and it's a set of exercises, and of course, I don't like the approach, but it's very popular. But I don't like either approach, actually. So what they're doing there is just a set of exercises, and you go through them. In some exercises, you just do something. In some of them, you have to invent something. You have to invent your own monads. Then you have to implement instances for them. And it covers a lot of things like lists, high-order functions, abstractions, and everything that you need. It is possible to use this resource for learning Haskell without mentor, but of course this course is meant to be used as a course with a lecturer, someone who tells you about that. Then CIS 194 is also very well known at University of Pennsylvania, Introduction to Haskell. I think it was started by Brent Georgi. I'm not sure. I think he was the first one teaching that course, but I'm not sure. Yes? Well, yeah. And it's really very good. And there are sort of very good lecture notes there with funny pictures. And they use Code World, by the way, at the very beginning. From the very beginning. Yeah, by the way, if you have any questions, please stop me any moment. I'll be happy to answer. Sorry that I didn't say that in the beginning. So the last version, which is available online, there is from fall 16, and it was taught by Joachim Breitner. He was at the University of Pennsylvania at that time. So it's also very good for self-learning. So some lecture notes, many exercises, many projects. So if you go to that course and see projects page, it is very good for self-learning, for ideas what could be done with Haskell. Yep.
You say for the people doing it themselves, we've been having them use Spring 13. The course has changed a lot over the years, but the one for people like self-learning.
Well, you mean, yeah, so that one from 13, I think it was published by Brand at GitHub. But I think they are very close. So this is this version 4.16 it used a little bit more. I think there were no lenses at 13 year for that 13 course, but there are lenses there, so they're a little bit different. So they were modified this stuff, but still you can use that version, and this version is good for that too. And then there is also very well-known Eric Meyer course from Delft University of Technology, and it is available at EDX platform. But Eric Meyer was very strong about teaching not Haskell, but functional programming instead. And at that time, when he was giving that course, he was very unhappy about changes in Haskell. Like, it was the time when they were making applicative subclass of monad, and it was awful for him. And then what was even worse, they were making all list operations functions as functions over foldable and not for list. So when you check the type of the function like map, you see all that crazy stuff about foldable and nothing about list. So he was very unhappy about that, and he said that I have to use hugs forever for teaching Haskell and never GHC. So that's he's very well known for that. So I think in Twitter there was a discussion like with hundreds of replies, and it was a very hot topic at the time. But of course, Eric May is great, and his course is also very, very good. We have many of books, and I don't like all of them. I have to say that, and that's why I've decided to start writing my own, and I don't like my own either. I'm sorry for saying that. But I like, by the way, I like the new book, Get Programming with Haskell from Manning Publications, which was published in March this year, I think. And it is very good for beginning Haskell programmers. And it's a book where you can see text data type from the very beginning, and you're advised to use that. And then there is also JSON encoding in there. So it's like a book on Python programming, but in Haskell. So you can do all that industrial stuff there from the very beginning. So I like it very much. But it's, yeah, and also I was technical proofreader for that book, so I'm a little bit tied to it. But yeah, we don't have too many books. So when I was trying to count all of them, I counted like 20, maybe 18, something like that. So not too many, especially in comparison with Java, C++, and other mainstream languages. And of course, we have many blog posts, and this is also very special for Haskell. So there are many things in Haskell which require writing blog posts. I think 90% of those blog posts are not about teaching something, but they follow the same pattern. Look, I've just learned very nice thing about Haskell. Let me tell you about it. So that's how it looks like. I think 90% of them. And then, of course, other people try to use that as a teaching material. But usually when you get that a week ago, you're never able to teach that in a good way. And that's what we have with all those blog posts. And of course, many of them are monad tutorials, and that's another topic. But even if it's not a monad tutorial, it's something like that. So I've learned something a week ago, so let me tell you about that. And that's why there are many, as they say, didactical problems with all those teaching materials. But then if you try to learn something, you just Google it and you have dozens of blog posts at that topic, and it's very hard to find something which is good. Or maybe impossible to find something which is good. And also for Haskell, we have very interesting educational, innovative resources. So this Code World for Haskell, which I already mentioned, and Chris Smith, who is doing a good job writing that Code World library package on Hackage for making pictures with Haskell, very simple Haskell. And then there is also typeclasses.com website. Julie Maranouk and Chris Martin are doing a good job discussing a lot of things in Haskell. I think it's a little bit overpriced, so you have to pay $29 per month to have access to their educational materials, and I think it's quite a lot, like for a month. And they don't have too many educational materials at that website, so it's much cheaper to buy all Haskell books and try to learn them. But it is quite interesting. They're using videos, they're using exercises, texts, and trying to teach Haskell in a good way. All right, and then now the main thing. Again, no breakthrough from me. So just pretty boring stuff about how I am personally teaching Haskell in my university. So the first question is how to start. And these strike out things is something which you never should say when you start teaching Haskell. Because when you say those things, well, Haskell is a lazy language. Well, so what? So you can get anything out of this information. Even if you try to explain this laziness, it's absolutely useless. So, and the same thing with static typing, with those abstractions. So if you say words like that, it's just bullshitting about Haskell. So, and this is a mistake which is very often made. So we know that Haskell is a tough language to learn. And one of the main reasons, as I see it, is that we've brought too many abstractions from mathematics without adopting them for programmers. Like, in fact, every programming language in some way comes from mathematics. Like, if you look at the Fortran programming language, the oldest one, everything there came exactly from mathematics. They just tried to Fortran. Do you know? I'm sure everyone knows, or not everyone knows how this Fortran is abbreviation. Do you know what stands for? Like formula translator. So everything comes from mathematics. They just tried to write those formulas in programming language. And all of them actually use all things from mathematics, from then theory of programming languages. But in Haskell, originally they've made a mistake. So this name, monad, it's a quite difficult word. And we know that it comes from Leibniz, from 18th century philosophy. And then we have these monads in category theory. And then we have the same name in Haskell. And then people always sure that you have to have a PhD on category theory to get that stuff. So I was teaching category theory once. I will never do that again because it's awful teach that stuff. And of course there is a connection between category theory and Haskell monads. Of course, some people say that it's a wrong connection. But that's not a problem. But the problem is that we use those words. And words in this world means a lot. So if it's a difficult word, then many people will think that it's a difficult concept. And it's not. and that's a problem. That's a gap between understanding and actual idea of this stuff. So okay, so we don't have to start with all that stuff. So we never mention all those buzzwords because they are meaningless for the beginners. But we could start with something like this, and this is an example of Code World IDE. So there's a website, and you can write it doesn't matter what it says there, but it's a simple program. It is a recursive program. There is a recursion there, quite sophisticated for beginners. But it's fine because you see in the very beginning that you can draw this picture. So it's a tree with lines here, and then you build all this stuff recursively. And if you can do that at the first lesson in Haskell, that's quite good. And you can grasp a lot of concepts here with this code. Again, so it's some combinations. So this is something close to semi-groups, for example, and then there's again a recursion, and you can do all that stuff from the very beginning. I am personally taking a different approach in my courses. I start with something very boring, you may say. So Newton-Raphson method for computing roots of equations like this. This is a task for computing a square root. I'm not alone who takes that approach. I borrowed that from the Structure and Interpretation of Computer Programs books, so they're giving the same example, of course in Scheme, and I'm doing that in Haskell. But why I'm doing that is because my course on Haskell for the second-year students follows the course on the computational mathematics. And they're doing a lot of stuff there about interpolating polynomials, they multiplicate matrices there, they integrate functions and stuff like that. And of course they also compute roots of equations. And that's why I believe that's a good example for telling them how good is Haskell and functional programming. And let me show you how we can start and what we could reach with this approach there. So the first solution, the first solution here is here, and you can see very simple functions, which are almost mathematical definitions, so they're very simple. And then this is Newton method for computing square roots. So and method is very simple. You just start with the first approximation. It can be almost anything, so guess. And then you have some criteria. Is this guess good enough? So is it a good approximation? And if it is a good approximation, then that's fine. You just give it back to the user. And if it's not good enough, then you improve it. And the formula for improvement here is, well, it's just an instance of a formula with derivatives, but for square roots, you can just give this formula and that's it. So we have checking whether this approximation is good enough, and we have a way for improvement. And we use that recursively, and when you show this function, you don't have to explain recursion because it's so natural here. So you just do improving and then try again checking this guess. So this is first function which I can write in Haskell, and when my students look at this function, they just see a lot of things about Haskell. They can see the way how we define functions using pattern matching. Pattern matching very simple here. But then this approach with some modifications could lead us to something very important. And the first thing is that, well, we don't have to compute only square roots. Why not computing cubic roots here with the same method? And then the idea is to turn this function to the higher order function, which is doing exactly Newton method, without square roots or cubic roots or everything like that. So we can arrive to something like this. So this is a higher order function, Newton, which takes a function for improvement and a function for checking. Like when we check, we have to square this value, or we have to compute cubic power of 3, or something like that. So we have to check. But then in this solution, we see that there are parts for square roots, and there are parts for Newton method. And this functional approach allows us to see clearly what is a Newton method. And when my students compare something like this implementation, with what they did in some imperative language in their course on the computational mathematics, they clearly see the difference. So they don't need that iteration there, while loops or something like that. And now they see clearly what is Newton method. Newton method is about checking whether the approximation is good enough and approving it. And that's it. There is nothing else in Newton method. And of course, it's much shorter than version in any imperative language. And you can write square roots like this. And now I can teach them with lambda functions here. And you can compute in the same way cubic roots. And everything else if you can come up with this formula for improvement. And it's just simple stuff with derivatives. But we could also use this approach, and I think this is the place where in structure and interpretation computer programs, they stop here. But with Haskell, I can go even further. I can show them another instance of the same Newton method with lists. Look, lazy lists, we can use that. When we are doing those approximations, we just go from the first approximation to the infinite list of approximations. And guesses here, it's just an infinite list of improvements, starting with the first one and then going to the infinity. And then we can talk about laziness at this point, at this first week of this course, and we can talk that quite right in this first week. And then you can see here improvement. You can see this check if it's good enough. And then you can introduce filtering. So we have this infinite list. We just filter out all guesses which are not good enough. And then we get the first good enough approximation. And I believe that this solution is much better in terms of reminding the real sense, real essence of Newton's method. So you have all these approximations, and you just take the first good enough approximation and you return it to the user. So we can see mathematics here, and we can see a lot of Haskell constructs in this code. And what is also important in this example, if you compile it in Haskell, it will behave good enough in terms of performance. So it will be compiled into something which is really a loop as an imperative program. So it's not like that quick sort example in Haskell, which is very nice, but of course no one would use it anywhere. But this actually can be compiled in a very good way. So it's a performant code written in Haskell in functional style, and you can use that in practice. And well, of course, if you want to use Newton method, of course, there are others for doing that stuff. But for Newton method, we could get quite good implementation in Haskell and executable. So that's what I'm doing the first week. And for speaking about this course, and in the first week, I can show them students something like this. I'm not implementing this stuff, so I'm trying to get to analyze string and find the most frequently used words there. And there are many steps. And in fact, I think that I don't have to say anything about this, because everything here with types is self-explanatory. You can see what I am doing here exactly from the types. So that's what types are good for. So it's not about functional programming anymore. So it's about types, type system, Haskell type system. But still, I can introduce all that stuff very quickly. And of course, I don't try to implement those functions there. So it's like more a prototyping. But I can tell things about that to the students, and they see clearly, well, this is a process. We have to do this, that, and that, and that. 4 steps, 4 stages. and then I can introduce function composition for saying, well, this is what I'm doing here, and just calling functions one after another using results of the previous call. So it's also high order function, and I can use that. So this is what I think important and what I try to tell you about. So when we are introducing language features, we have to introduce them for something. We don't teach Haskell. We're just trying to solve our problems. And those language features are just very convenient for doing that stuff. So that's how I believe it is a good way to introduce all of them. And there is another part to this creed. In fact, I think many people try to use Haskell for testing mental abilities, and that's not a very good thing, actually. It's not about that. It's about useful abstractions. It's about useful things. It's about something that can help you getting your job done, and not about testing you. So many people in Haskell community, or some people in Haskell community, try to show how smart they are understanding all those things. And sometimes this leads to a very toxic behavior within the community. So that's one of the serious problems within the community. So this is my sort of syllabus for short 6 weeks long course in Haskell. So it's like 6 weeks and 6 topics which I usually talk about in that course. And the idea for this course was as follows. So I think for 7 or maybe 8 years, I was teaching Haskell for the 4th year students, senior students at my university. And then there was a chance and it was 16 weeks long. And then there was a chance to move to teach Haskell to the 2nd year students. And well, I was one of the people who decide that. So it was not something that someone told me, do that and do that. So I was among those who decide whether to switch from 16 weeks course in the 4th year to the 6 weeks course at the 2nd year. And it was my decision to make that move. So I believe 6 weeks at the 2nd year, that they are much better than 18 weeks at the 4th year, because they have more chances to get closer to Haskell after 2nd year. So that was my decision to switch to this form. So for the important part here, so is it possible to teach monads? Of course, I'm pretty sure that it is possible to learn monads. I know a couple of people who get that in a very good way. But the question about teaching monads is actually, it is not clear to me. So everyone has their own road to monads, and as there is a great book, Road to something with Haskell. So the problem is that it is not clear what does it mean to teach monads, and it is unclear to me what does it mean to know monads. So what does it mean? How to use monads? And we can teach that very quickly with maybe, either, and other IOR and other simple instances. Or how to implement monads, how to invent monads by themselves. Like many blog posts, many monad tutorials, they are trying to teach you inventing monads. I don't think that that's a good approach for that. Well, because you're not inventing monads, you're inventing some pretty engineering tool. Like you start with some dirty code with checks whether it's just something or nothing, and then you try to refactor it, and then in this process you invent monads. But you're not inventing monads, actually. You're inventing something simple, some tool for making your code a little bit shorter. It's not it's not a monad. It's just one instance of a monad for maybe. So you can invent that instance, but you can never make this step of abstraction from this instance to the monads. And then there is also this thing. So there are many people who say, well, I don't understand monads. Please explain me monads. And I hate that. You know, there is a great Stack Overflow question. What part of Hindley-Milner do you not understand? And there are great answers there. So that's something. Well, what does it mean to understand monads? I don't know. So I know how to use them. That's fine. Well, how to implement instances for your own monad? Well, that's fine. But what does it mean how to understand that? How to understand category theory? I don't know what does it mean. There is no clear meaning for understanding. So I never teach understanding. And again, if someone tells you, well, she knows how to teach monads, how to understand monads, I never believe them. Well, maybe because I just don't know, I can't get that in my mind. But what I am doing, so I'm starting with I/O, and with I/O, working with files, with very simple problems like read file and then output something. And here we can see that this I/O is used at a type level for distinguishing pure code and impure code. And this is a very important idea. So we have two kinds of code, and we want to distinguish them because of good properties for pure code and not that good properties for impure code. So we have two sorts of computation here, pure and impure. And then I/O at a type level is a good thing for distinguishing them. So you can show that there are no function which takes I/O A and gives you A. And of course, we know that there is that function, but you never tell that to the students. They will definitely find that function by themselves. That's for sure. But I never tell them the name of this function. Then I go to the random numbers. And random numbers are also a very good example. Because everything there is pure. But you have to carry that standard generator with you all the time. And the only moment when you need I/O, and at that point it's very clear why you need I/O right there, is when you want to get a standard generator from your operating system. So that's the entrance clear and one single entrance to the real world. So this is also I/O monad, but it's again this distinguishing between pure and impure code. And then what I am doing, I am talking about computational context. Some people say that the idea of computational context is unclear. Well, I'm trying to make it clear. And in fact, most of the people, if they come with some knowledge of mathematics, they know what does it mean. So there is pure computation, and then we can do something with that computation. We can use effects for input-output. We can get the idea of computation with potentially missing results. I mean, maybe. Missing result with some explanation what went wrong, like either. And we can have non-deterministic computation here. For many people trying to learn Haskell, non-determinism and least monad is very difficult because they don't used to this idea of non-determinism. For my students, it's not a problem because before that stuff in Haskell, we have a theory of computation course, and we have a non-deterministic Turing machine there. And when they know that, it's not a problem to talk about non-deterministic monad in Haskell. So it's somehow a little bit easier for me. So I'm talking about that. And I also talk about a value and a value in a context. At the type level, so we can see this is value integer value or string, and this is string in some monad, in some context. So just you can see that at the type level they are different. And this is also a very important idea. And then I am doing something very traditional. So functor, and always when I'm talking about functor, I start with type class. And only then I give specific instances. And I think in most of blog posts, they start with some specific instance. And when you start with an instance, I think that you are losing this idea. So this idea, abstract thing, abstraction, monad as a computational abstraction, is something which is much more important than any specific instance. And when you start from abstraction and go to the details of specific instances, it's much better approach, I think so. Yep.
So what do you do when people come up with unsafe perform IO? You said you don't tell them about it, but you said they end up finding it. So how do you kind of address that? How do you talk about that? Don't use that.
Well, the name of that function is very good, and it is very good for reason. Well, you can use that, but it's unsafe. So that's I'm not trying to get into the details.
Is that enough for your students most of the time? I mean, do they kind of say, oh, well, here's this one, and because I mean, what you said earlier suggested like, oh, maybe they do find it, and then maybe they just use it anyway because they couldn't figure it out any other way, or again, I'm just wondering what your experience is with that.
Well, yeah, just saying that it's not a good. At this point, when it's a beginner, it's very difficult to explain why it is not a good idea to use that.
Yeah.
That's very difficult. I think that's impossible, and that's why they use this name, unsafe.
Mm-hmm.
So maybe later you can show tricks when, like, I like an example when they use unsafe perform IO for things to get around with type system. They're trying to do something with that, something wrong within type system, but they can do that. So say, well, it is possible, but why choose this path? So something like that. But for the beginners, it's impossible to explain. Or even if you try to explain that, they will never believe you. So that's something that I don't know how to say them. How
you
to
just tell them, just don't.
Yes. Well, this title is just explains itself. So, but going into details all the time is a very big problem, because they just miss all those details, and then, well, sometimes it's better to say, well, never use that, or you will never get a point for this task, like something like that.
Yeah.
For students, that works very well. All right, so yeah, and then this approach with lowers with limitations, of course, it's very important. It's pretty standard, so you can use functor for this and that, and then you cannot use that for that. Yes, please.
Sorry, I was just curious. You said that you don't want to give an instance as an example before giving the instruction, but I mean, are you doing that with I/O though?
So before that, so if it's a lecture number 5 or 6, before that I have algebraic data types. So I'm introducing maybe and either as algebraic data types, and I don't have to say about them as a monads. But here, of course, I can use them as an examples of computational context. They are very important. So for computational context, I'm using IO, maybe either lists, and I think it should be 5. Maybe I forget something. So I use them, of course. I need that because there should be many instances to be something that students believe. So and then there are limitations, and then I go to applicatives, and I am using modern style when all of them are subclasses of each other. So just as doing the right thing. And if they use older compiler, then I just say, well, just make sure that you know that they are actually goes in this way. And I was very happy. So there was a voting within the community whether to, I think some years ago, whether to do that stuff, whether to make applicative a subclass of monads. And as an educator, I voted for, because I like good things to be done. And I don't care about backward compatibility and stuff like that. I don't write Haskell programs professionally, so I'm not interested in that. So it should be a right thing, so I voted for, even if I had to change some of my educational material, some of my slides, that's not a problem. So yeah, and this is the end of the 6 weeks course. So I'm finishing with monads, and that's it. I believe that's enough. So it's not just functional programming, but it's also something about abstractions and programming. And when I taught 18 weeks course, I was trying to talk about all this stuff, like many topics. Sometimes I meet something, sometimes I give them something, but it's for fourth year students. And at the end, some of them writing projects with which use like Google Maps and some messenger boards and something like that to unify them in one project. So they use everything they can do in any other language with Haskell, using all this stuff like concurrency and everything. So it was possible there. Okay, so just for the last example, I want to show you this library. Like 2 weeks ago in Boston at Haskell Meetup, I was talking about logging. Well, because it's logging, that was a chapter that I was writing at that time, chapter for my Haskell in-depth book. And I gave them an example of this very simple logging library with the name colog. And I like it as an educational tool. This is what this core means there. It's quite new. I think it was started in October or even November this year, so very new library. But now it's quite powerful already. And there is a good blog post in English, of course, explaining that library. And it uses an approach which I like very much. So this is it. Like logging is a monadic function. So when you look at other logging libraries, well, it's not like that. This is, again, an essence of logging. It's some function in some monad which is able to record something, some message. So that's it. That's a logging function. And then they use new type for that to be able to write some instances. So which instances? For example, yeah, this is a simple example of logging function, just logging to the standard output. That's it. It's very simple. And then here, you can talk about composability with semi-group instance. Because what does it mean? Logging to two different destinations, standard output and standard error. And that's fine, just semi-group instance for that log action new type. So it's something, semi-group, that we need for writing logs to two different sources. And it's composed very, very well here. And what I like the most of that library is how they are using contravariants there. So it seems like logging is a very good example of contravariant functor. Because if you can log B, log something of type B, then in this case, this is it. So you can log B, like this type. And you have some A, and you can transform A to B. Then that means that you can log A. Well, you just simply take this A, transform it to B, and then log B. And that's contravariant functor. So that's what they are for. That's a very good example of that. You don't have to talk about category theory here or anything. So just logging, very simple. And in that library, they use that a lot. So they just introduce this not as a hard concept, not as something very difficult thing in Haskell, but just a very natural thing to getting your job done, to get logging. And then they also found a way how to use other classes there, like divisible and decidable. So what they're doing, you have a huge complex data structure, and if you can divide it into several pieces and you can log them independently, then you can log the whole structure again. So these concepts arose also very naturally, and you can use that, and it's very practical. So this is a very good library, and I recommend looking at it. So quite new. So bit.ly/colloq. That was that link, or you can find it there. So and I like this library because it follows the same approach. If you need to teach something in Haskell, well, just come up with a good practical example, and then you can teach that, and everything will be understandable, and you don't need anything else. So that's it. What I was wanted to talk about here. So thank you very much. I'm happy to answer your questions.
I was wondering, do you find that the students after the 6-week program have opportunities to use what they learned? Like, do they use it in other classes, on projects? Just wondering, like, what next?
Well, some of them definitely use that. That's for sure. And but what I think the most important goal for that 6 weeks course is the ability to use functional features in other programming languages. So of course, most of their projects later they are done in C++ or Java or in C#, and then they don't have a fear of using functional stuff like high order functions, and like link from C# is very used to them because they did all that stuff with lists and Haskell. So I think that's the main aim. I'm not aiming them using Haskell for doing. Some of them do. Or some of them go and then choose me as an advisor and use Haskell with me. But most of them don't use Haskell. But they know this idea, and I think that's enough. So mainly functional program, functional features in other languages. So that's what's my aim there.
I like your idea. Your high-level idea seemed to be one of the main issues in teaching Haskell is that as PL people we have all these we're excited about all the cool like mathematical, semantic, abstractions, all these things that are like kind of deep and technical, and you're basically saying like, yes, there's all that stuff, but like that's not a good way to present it to people, right?
Exactly.
Instead, if you kind of it's just like your logging contravariant thing. It's like instead of saying, oh, look, it's a contravariant functor, which is a mouthful, you say, oh, this kind of makes sense, and you kind of like try to bring it across in like a way it's very kind of as you use it, and like kind of more try to hit the intuitions and that sort of stuff, and like try to push away any of the kind of deep kind of really understand it. Like you're thinking about monads, you don't want to try to understand. Anyway, I thought that was interesting, trying to make it more approachable. I think it's kind of the idea.
Yeah, exactly. You described that very well. And so my problem is that I know category theory. I know theory of programming languages. I know all that stuff about system F and denotational semantics and all that stuff. But I don't think that all that stuff is useful for Haskell programmers. And I think that it's not just useless. It can bring a lot of harm there because of the additional complexity that they don't need. So that's why I'd like to get rid of all that stuff.
Yeah.
Are any of the materials from your 6-week course available publicly, or are those things that are restricted to the class?
Well, it's not restricted, but it's everything in Russian. So I'm teaching that in Russian. So yeah, yeah, I'm trying to use something from that, but for Haskell in-depth book, of course, it's not something that can be used in that book directly because, well, it has different ideas there. But yeah.
So I also really liked the idea that first you should present the students with a problem that they think they want to solve, and then show them the language feature that solves that problem. I was wondering if you do that with I/O, and if you do, how difficult you find it to convince them that I/O is a problem worth solving.
That's a good question. So whether this I/O is a good thing, actually. Well, My motivation is quite simple. So first, I try to convince them that it is really a different sort of computation. So with I/O and without I/O, they are different. And they are different because I/O is not something which is done in mathematics. And for describing something different, you use something different. And that's pretty natural. Like in programming, from the very beginning, they are taught not to use the same variable for two things. So if you want to do different sort of computation, why not to use different type for that? Why trying to combine all that stuff? So that's the first thing. And the second thing is that, well, you do want to control different things. So you do want to be sure that in this function, you are never doing some unsafe things, like that you never delete the file in this function, that you never destroy the world in this function. So that's another thing. So of course, they all know that in other languages they are not doing that stuff. But that's how Haskell is different. And they should be open to learn new languages and new ways for doing things. So there are positive motivations, and then there are also negative motivations, like you just do less mistakes with your code when you can control pure and impure parts. So that's how I'm getting around that.
Thanks.
Well, just after 12, so let's wrap it up here. If you're interested in coming to lunch, just let's go there. Let's thank Vitali one more time.
Thank you.
Drop these off.
I'll laugh at your next joke.
Okay, I'll send you an email.
Only if it's funny.